And now Wenhao will tell us about whether or not we can reduce structural subtyping to parametric polymorphism.
So hi, I'm Wenhao. I'm a PhD student. I'm a PhD student from the University of Edinburgh, and I'm going to talk about something very simple, something about how to encode subtyping as polymorphism. And this is joint work with my collaborators. Some of them are sitting here. Yeah, so we consider structural subtyping, which means the subtyping relation is defined inductively on the structures of types. And one most common usage of structural subtyping is to allow the extension and restriction of records and variants. So this can also be done by using role and presence polymorphism. So since these two features were proposed, there have been a lot of discussions on the similarity and differences between them. For example, in one of the initial papers on role polymorphism, Michel compared his system with another system using subtyping. And he gave some examples that are well tapped in one system, but are ill tapped in the other one, and vice versa. So the expressive power of these two specific systems cannot be compared. And later, François Potier wrote in his thesis that these two features actually complement one another because they are useful in different situations, and it would be great if you have them together. And Andres Jusberg, sitting there, commented in Lambda the Ultimate that subtyping is in fact a Pullman's rule polymorphism. And I agree with him because most basic usage of subtyping can also be done by rule polymorphism, and the latter works much better with type inference. And there are still more and more discussion going on if you search it using Google, but there still lacks a formal study on the expressive power of these two features. So we want to fill this gap partly because we are more interested in how to encode subtyping as polymorphism. Okay, so let's start with the simply typed lambda calculus. It has term variables, has lambda abstraction, lambda application, and we can extend it with variant. We write the square bracket for variant. So here we have a variant age. It has the label age with the integer 42, and there is only one label in its variant type. And we have a function getAge. It takes a variant that can either be the label age or the label year, and it calculates an integer from them. So there is an obvious type mismatch between the function and the variant. What we can do is we can extend the calculus further with subtyping. We call it simple variant subtyping. It allows us to extend the labels in a variant. So we have this triangle for the explicit upcast. We can upcast the variant age to a bigger variant type with two labels and apply the function to it. Yes, so this is simple subtyping because we only consider the subtyping of variants. And then later we will also consider strictly covariant subtyping, which means you can propagate the subtyping relation through strictly covariant positions, like the result type of a function. And we will also consider false subtyping, which means we can also propagate the relation through contravariant positions, like the parameter type of a function. So it is well known in the literature that we can simulate this kind of upcast using some destruction and reconstruction. So here we can simulate the upcast of the age by using the kit split to split it, to destruct it, and construct a new variant with a bigger type with two labels. And this not only applies to simple subtyping, but also applies to false subtyping. It is known as the coercion semantics in the literature. Yes. And another direction of extending the calculus lambda variant is to add role polymorphism, which also somehow allows us to extend the variant type. So here we have the variable role, which abstracts over other labels, and we can instantiate the variable role to the label year to add the label year to the variant type of this variant, so we can simulate the upcast. This works well. This gives us a local type only encoding of the upcast. So the idea is we use instead of using the variant destruction and reconstruction, we use the type application and type abstraction. So we first adding the label year to it and abstract it to make it again a polymorphic type. This is important because what we want is a uniform translation. So we need to make sure that every variant type is translated to a polymorphic variant type, including the function parameter of the getAge function. So we need higher rank polymorphism. And we call it a type-only translation because it only introduces some new type abstraction and type application. In other words, it is actually identity after type erasure. And we believe this is very important if we want to compare the expressive power of two type features. Yes, so this is the story for variant, and we have a very similar story for record because they are kind of dual to each other. So here we extend the calculus with record, we write the angle bracket, and we have a record Alice with two labels, name and age, and we have a function getName. It takes a record with only one label and uses the projection to get the name from it. And again, there is a type mismatch, so we need to add subtyping. The record subtyping allows us to restrict the labels in a record to a smaller one, so we can upcast Alice to the record type with only one label. Yes, and again, we can simulate it by using some record destruction and reconstruction. So we use projection to get the label name from Alice and construct a new record with only one label to simulate the upcast. This is well known. And we can also extend the calculus with presence polymorphism. So here we have two presence variables, theta 1 and theta 2, they abstract over the presence of the label name and age. Then to remove the label age from the record, we can just instantiate the presence variable theta 2 to absent. So this gives us a type-only translation of the record, of the simple record subtyping to presence polymorphism. And it's very similar to the previous type-only translation. We first use type application to instantiate the presence variables in Alice prime, and then we abstract over it to make sure that it is still a presence polymorphic record type. And we also need a polymorphic type for the function parameter, so we need higher rank polymorphism. Yes, so far so good. We have used the row polymorphism to simulate variant subtyping because they both allow some form of extension. And we have used presence polymorphism to simulate record subtyping because they both allow some form of restriction. The natural question is, can we swap them? Can we use row polymorphism to simulate record subtyping? At first glance, it seems possible because for record subtyping, what we want is we want to remove some labels from record on covariant positions. This is actually equivalent to adding more labels to records on contravariant positions. So consider the previous example. We can translate the record Alice to itself, translate the function to a row polymorphic function. So it is row polymorphic, and the parameter has a row variable which can be instantiated to other labels, so we can extend it. And the function application and upcast is translated by instantiating the row variable of the function to the missing label age with type int. So we can resolve the type mismatch. But unluckily, we want a compositional translation, which is the macro expansion. So, but this translation actually breaks the compositionality because when we are translating the function application, we only know the translation result of the function and the translation result of the argument. So we can only look at some local information. But to know that there is a missing label age with type int, we need to globally look at the whole structure of the original term. And this breaks the compositionality. And moreover, we formally proved that there is actually no type-only translation from simple record subtyping to row polymorphism. and similarly from simple variant subtyping to presence polymorphism. And the idea of this the idea of the proofs of these negative results is to find some good counterexamples and try to define a very general translation scheme for them. And then you can try to show some contradiction. For example, it is contradiction to the compositionality requirement, or it is contradictory to the type-only property or something else. But we still have one hope to make the translation compositional. The problem is we don't know that there is a missing label age with type int, but in practical languages, we usually have type inference for polymorphic types, and the type inference knows it. So we can just define the translation as the erasure function. We erase all type annotations and erase the explicit upcast. And the type inference automatically infers a polymorphic type for the function. It is a real polymorphic type as we have seen before. And when you are doing the function application, it automatically instantiates the real variable to the missing label age with type int. So it works quite well. It works not only for simple subtyping, but also for full subtyping. So this is the calculus with records, and for subtyping, we write the for as the superscript. And to make sure that the type inference is excitable, we restrict the target language to rank 1 polymorphism. So we write the number 1 besides the variable rule. And as a result, we have a similar restriction in the source language. We only have rank 2 records, so we write the number 2 along the record. And the way we define rank n records is very similar to how we define rank n polymorphism. And please check the paper for the details. And we have a similar result for rank n presence, for rank 1 presence polymorphism, and a similar result for variants. So here is the full picture in our paper. I have only covered part of them. So in the paper, we also have some translation of the strictly covariant subtyping and full subtyping in the setting of explicit calculus. And we found it very surprising that the symmetry is broken when you are considering more involved subtyping. Yes, and in the paper, we have proved all the errors in this figure. We have formal definitions and some meta-theories, like the translation preserves types, the translation preserves the operational semantics, and and some proofs of the negative results. Yes. And I think I'll finish. And there is some takeaway. So first, in explicit calculi, we found that even if you only want to encode simple subtyping, you already need some higher rank polymorphism. And for simple subtyping, as we have seen, there is a very good symmetry between the results of records and variants. But the symmetry is broken if you consider some more complicated forms of subtyping. And we have proved that there is no type-only encoding of full subtyping. But for languages like OCaml, it has type inference, so it can actually encode a restricted form of full subtyping. Thank you.
Okay, we have plenty of time for questions. Please come to the aisles if you have a question.
So, I have some principal question, because regarding your first takeaway, you say actually subtyping, even simple subtyping needs higher rank polymorphism, so which sounds like a little bit hard thing, right? But subtyping is everybody knows, every Java programmer knows. So does that mean actually subtyping is the right way of doing things in practice?
Well, I don't know. Personally, I don't really like subtyping, and so that's why I want to encode subtyping using something else. But it is sad to say that even if we only want to encode simple subtyping, we need some very complicated mechanism of polymorphism. But I think the point is, in practice, most simple usage of subtyping actually it's quite shallow. It doesn't have a very complicated structure. So Yeah, so it can be done by some lower rank polymorphism.
Okay, thank you.
Yeah, so thank you for the talk. You said about the translation for records that it was not compositional, right?
Yes.
So does that still hold if you do the translation on typing derivations? It seems the information is there in that case.
Yeah. That's exactly the way that we do that we do translation. The translation is defined on the typing no, it is only defined on the on the bottom typing judgment of how to say. Yes, it only defined on the bottom typing judgment of the term. But I don't think if you have the full typing derivation tree, you can have a compositional translation because it seems not so clear to how to get the missing label from the derivation tree. Maybe you need some very complicated algorithm to retrieve this information.
Yeah, okay, I'd have to look at it in detail. Thank you.
Yes, okay, thank you.
Your talk offers an interesting point of view of subtyping in the sense that it focuses a lot of a half of subtyping. And like in many languages, we think about subtyping most as the behavior may change between two subtype more than just, yes, you can have more methods. Is there a terminology that you have encountered while doing your research to distinguish those two kinds of subtyping?
Yeah, well, I'm not sure, but I guess what you mean is nominal subtyping, which is like the classes structure. Did you mean that? Yeah, so here we consider the structural subtyping, which is the most common example is the record and the variant. You are just define the subtyping relation on structures. Yeah, but I'm not sure. I don't think nominal subtyping can be encoded only using something like polymorphism. You may want to have some constraints like qualifier types or the type classes in Haskell to encode that.
Okay, well, let's thank Wenhao.